Welcome everybody. Today we have our guest lecturer, David Fridovich-Keil. David is a professor at UT Austin. He did his graduate school at Berkeley with Claire Tomlin and then did a postdoc with Max Schwager at Stanford. David's worked on a lot of different kinds of projects, I guess all kind of in the area of controls, autonomy, machine learning. And he did a wide amount of exploration and has now found himself kind of focusing, at least now, on dynamic game theory and really thinking about multi-agent interactions. I know that you all have been reading his text on smooth game theory as well as his some of his most recent work, and I believe he's going to be covering some of that today. So, without further ado, David, please take it away.
Sure. Thanks, Sylvia. It's great to be here. Yeah, so I guess let me just kind of first explain like a bit of the structure of the lecture I have planned today. So the overall topic is going to be this related to this paper that I hope you've had a chance to read, autoencoding Bayesian inverse games. So it's just from last year's Wafer, which if you're not familiar, I'd highly recommend Wafer as a great publication venue. It's a very fun conference. So anyway, that's what I want to tell you about is this paper. But in order to kind of highlight, first the problem we're solving and the kind of showcase some of the techniques that I think are elegant that we're able to deploy. I want to first give you some sense of what are these problems and what are those techniques. So the first part of the talk is going to be almost like a tutorial. So hopefully it's useful for folks who are less familiar with the area. And if you looked through the kind of course notes, the little monograph that I sent Sylvia to pass on, that smooth game theory text, it will be very familiar, but there will be some things that are not in that text. So anyway, that's the structure for the talk. Please do interrupt me. This is already kind of getting towards the end of my day, so I'm on the tired end, and I'd love to keep this interactive and not just be droning on at you. So if I'm not seeing your hands raised or whatever, just jump in and get my attention. Okay, so that's the plan. All right, so first off, we're going to talk about games. Games are everywhere. You can find them literally anywhere you're imagining there to be sort of multiple decision-making agents in a similar kind of shared space. Could be a physical space, could be kind of a virtual space. In this talk, we're going to focus on kind of driving and traffic as kind of just the easy to understand application that hopefully everybody can connect to because everybody's been in a car. So that's on the left, but there are other examples that I think it's not hard to imagine the same types of techniques deployed. So we've in my group we've worked on like air traffic management as one application area. I haven't worked too much with power systems on the kind of top right, but I think that's another interesting area to deploy these types of algorithms. So kind of zooming in on traffic, um, this is actually how I got into these problems. I was thinking about motion planning in autonomous vehicles. So if you imagine you're on the motion planning design team for an autonomous vehicle, let's say this sedan I've highlighted, what you typically think of is some version of model predictive control. So what that means is you understand you have a physical model of how the vehicle can move. So that's big F of XU equals 0. X here is kind of the indicating like the sequence of states that the vehicle will occupy over time. EU, I'm indicating the sequence of control actions, the signals you'll send to actuators over time. And so there will be just some algebraic equation that relates those variables that tells you when everything is consistent with physics. And then there will be some initial condition, you know where you are, and I'm calling that x hat. So if you kind of enforce that at the first time step, x1, you're at this known position, known state x hat, that's also a constraint that you would want to enforce. And then there will be some objective function j that maps the, where you're planning to go and the actions you're planning to take to some number. And the smaller that number is, the least, the less costly that trajectory you're planning. So that's the kind of typical viewpoint for decision making in autonomous vehicles and many other cases. Um, so where do games arise in this picture? Well, it's not too hard to see that cost or maybe some of the constraints you might have that I didn't write down, let's say collision avoidance or things like that, depend on where you think others are going to be in the future. So what I'm doing here is I'm highlighting two other vehicles and saying, okay, well, if car one wants to make a lane change, how good or bad Agent One, Car One thinks a planned trajectory is depends upon where they think Agents Two and Three and any other cars on the road are going to go. Okay, so those factor into the problem. I've highlighted them in blue. And in the if you look up literature for this stuff, you can look up like autonomous vehicle prediction or whatever you want on Google Scholar. You'll see a million papers, um, and people throw all kinds of tools at this problem. So what I'll kind of argue though is that actually taking a step back, like look at this picture. I'm highlighting three cars. Like there are drivers in those cars, and those drivers are, ideally intelligent decision makers. And so X2 and X3 here are not just things that I can predict kind of uh, a priori. What I should actually need to understand is that those are, those trajectories that these other cars are going to drive depend upon decisions they're going to actively make, and those decisions depend upon like what I do, right? Because if I drive a little bit, they're going to see where I drove, and then they're going to make a decision about what they do. So that kind of leads me to expand the picture to look like this. So all I've done is copy pasted the same problem three times and changed the indices to match the players. So what I'm saying is that, hey, agent one's problem depends upon what it thinks agents two and three are going to do. Agent two's problem depends upon what it thinks agent one and three are going to do, and so on. And all these decisions are coupled in that way. So what just happened? Well, basically, I took an optimization problem, an optimal control problem, and I turned it into now a three-player game. Each player has an objective, each player has some constraints. Maybe you even have more constraints that I didn't write down, like they want to avoid collision with each other, as an example. But the bottom line is we got a game because we realized that Agent One's problem depended on decisions that were being made by Agents Two and Three, and vice versa. And so that coupling induces a game. So that's kind of at a high level, like where you can see these types of games arising. Hopefully it's clear. Um, so I guess if there are no questions, what I want to do is tell you a little bit about how to think about solving these problems. This will set the stage for the meat of the talk. Okay, so are there any questions?
I have a quick question for you.
Yeah, fire away.
I'm curious what you track inside your state that you define as X. Like what kind of like real world things do you track?
Yeah, that's a great question. It's funny you ask. I teach the undergrad linear systems class, and I was just having office hours out there, and somebody was asking me pretty similar question. And so what I told him, and I'll tell you, is kind of the formal understanding of what is a state is it's the collection of information you need in order to predict how that information will evolve over time. So basically, uh, like as a concrete example, if I keep track of the position, the heading angle, where's the front wheel angle with respect to the body, maybe that's enough information to predict how all of those variables will evolve in a split second. So on the other hand, if they depend upon, let's say, um, the angle of the road, then I also need to keep track of the angle of the road.
Mhm.
That needs to be a state variable. So the state is basically the collection of information that you need at time zero in order to predict how all of those pieces of information will evolve in the future. And basically, when you write down equations of motion for any physical system you like, there will be a procedure for constructing the state.
Okay, gotcha. Yeah. So it might not be commonplace to just track like XYZ and like your orientation or something. Like there might be something else in the state you want to.
Yeah, yeah. Or like, let me give you another example. I TA'd the intro robotics class as a grad student, and I remember there was a student in the class who was doing some research on the side in a group that was doing like computer vision and robotics.
Mhm,
And he asked me, "Hey, David, so I've got this camera on my robot, like or looking at my manipulator arm. Um, is the image that it returns to me a state of the system? Like, is that something I can
mhm,
consider to be the state?" The
mhm,
answer is no.
mhm,
Why no? Because the image tells me, like, sure, I can, if I'm good at detecting, stuff in images, I can figure out like what the joint angles are and stuff.
mhm.
But I certainly don't know how the joints are moving. So if I imagine like fast forward like a quick fraction of a second, I have no idea if like the arm is moving this way or if it's moving down. All I see is where it is now.
Mhm.
So if I can't consider just a single still shot of a robot arm to be a state of that system, but maybe um, seeing a sequence of frames over time might be a valid representation of state.
Yeah, you need that additional info. Yeah.
Yeah.
Huh.
So it's a bit of a subtle concept. The state is not kind of unique.
Mhm.
Typically, so there can be many valid representations of state for a system. So it's a whole thing. But just for now, for the sake of I think this talk, you can take X to be kind of any valid representation of state for your system.
Gotcha. Thank you so much, David. Appreciate
Yeah,
it.
for sure. Any other questions?
I have one question.
Yeah, go.
Yeah, so just to make sure that I understand your formulation of the constraints, so the x1 and x hat, so x hat is your estimated position, and your x1 is your like actual position, or is it something different?
Yeah, so by position, I'll substitute state, but sure. And then the superscripts are denoting players, and the subscripts are denoting time. That's the other piece here. And then the bold is denoting aggregation over time. Hopefully, it's not terribly important to this the rest of the talk, so I kind of didn't want to dwell on it, but yes.
Okay, so the hat represents estimates.
Yeah, yeah. The hat is just some known constant, just estimated state currently, if you like.
Got it. Thank you.
Could I ask a quick question?
Sure.
Um, I was just curious about. I understand that we have, initial conditions and initial states for all this stuff, but I was just curious, like in an actual real life scenario, are these initial conditions often just like the first point of data? For example, if you were given, this image that you were using in the background, would it just
Mhm.
be like the instant the camera is turned on, or whenever like something is
Oh,
agent one is entering the
yeah, yeah, yeah.
background?
So I'm imagining like time one is the present, and time two is whatever time discretization you care about after the present. So X1 hat, X2 hat, X3 hat for three players. Those might be so those might be like estimated states for those vehicles at the present time, time one. And so where might those come from? Well, surely like this isn't, I mean, maybe this is the moment we fired on the camera and started caring about this problem. But in general, it's at some intermediate time of operation of, we're driving along the road. We didn't just start here right now. And so you'd have some kind of localization, mapping, filtering kind of software going on. So basically think like glorified Kalman filters. And those Kalman filters would be telling you some state estimates.
Gotcha. Very cool. Thank you.
Other questions? All right, let's get to the good stuff. So, how do you solve these problems? This is like a whole area, and um, I don't mean to imply with the what I'll tell you that this is the only way to think about it, but I think it's the simplest and the most useful way from a more practitioner's perspective. So that's why I like it. But let's kind of go back and think about those coupled optimization problems I had on the last slide. Um, okay, so it's a bit tough to do this not in person, but just maybe like use the like Zoom raise your hand feature if you have taken an optimization course. Okay. Uh, what fraction of people is this? Let's see. Okay, not a big fraction, unless people hands have disappeared. Okay, all right. So in that case, a lot of what I'm about to say is gonna probably be a little faster than I would have liked, but we'll roll with it. So okay, hold on. Let me minimize that window. All right. So okay, so for those of you who had your hands up, um, somebody shout out. Like, why am I talking about on the left? I have the second bullet that's saying to first order, basically, if players are happy, if every agent is happy, they need to be satisfying their KKT conditions. Can somebody tell me what I'm talking about? Anybody know what KKT conditions are? Want to explain it? Okay. All right. No, okay, go for it. Go for it, please.
I think KKT conditions are sufficient and necessary conditions for a global optima. So you have something to do with the primal, something to do with the dual, and then you have some slack conditions.
Yeah.
I think complementary slackness.
Exactly. Yeah. So that's the basic idea. Now, just to maybe clarify, so in general, I haven't told you anything about the structure of J, the structure of F. So in particular, um, yeah, there's a whole kind of subtle structure here, but without going into too much depth, the KKT conditions are basically first order conditions. They only depend on gradients. And they're necessary for optimality under some conditions. So those conditions are called constraint qualifications, and that's a bit beyond what I want to talk about today. But under some conditions that you may care to look into if you ever wanted to dig in, these conditions called KKT conditions are necessary for a solution to be optimal. They're not sufficient in general, and so they're not even sufficient for you to be locally optimal. So what you need to be locally optimal is you also need kind of the local kind of curvature of J to be kind of convex. You need to know that you're at the sort of bottom of a bowl, not the top or a saddle. So that means you need second order information. And then okay, so the point is KKT conditions are the starting point, they're not the ending point. But if you open up like any optimization textbook, here's like the one I kind of always jump to at first. So if you open up an optimization textbook to a random page, okay, I picked a bad random page because I don't see the letters KKT. But the bottom line is, if you're opening up the book, pretty good chance you're going to be seeing an algorithm that's based upon satisfying KKT conditions. What are the KKT conditions? So the KKT conditions are basically saying that at a solution, the derivative of the objective is parallel to the derivative of the constraints. So basically, it's saying that the pressure exerted by minimizing the objective is exactly balanced by the pressure kind of exerted by the constraint to keep you in the feasible set. Okay, so that's condition one. Condition two is to say all the constraints need to be satisfied. Okay, and condition three is to say that these things called Lagrange multipliers, if you have inequality constraints, here we don't have any because I was lazy, but maybe we have some. Lagrange multipliers for those constraints can only be positive if the constraint is satisfied with equality and otherwise vice versa. So if the constraint is not satisfied with equality, it's sort of strictly satisfied, the multiplier should be zero. that's what the three KKT conditions are, the three types of conditions. And so anyway, the upshot is we know these are necessary conditions from basic optimization. And so in this case, there are n players, and each of them has a problem. The problem depends upon what the other players are doing. But like if all the players are happy, we're at a Nash equilibrium, then all those KKT conditions had better be satisfied. It's a necessary condition. So I'm going to write all those conditions down, and it'll look something like this. Okay. So basically, stack them all up, and there's going to be some big, maybe wildly nonlinear complicated function g of all the variables, the primals x and u, and the dual variables, the multipliers lambda, that is equal to 0. Okay. So we're not going to need to dig into actually the structure of what's going on in these KKT conditions for the rest of this talk, but that's where they come from. Okay. So now in order to solve this problem, solve the KKT conditions, we're basically realizing that this is a root finding problem. There's some function g, it depends on some variables, and it better equal 0. I'm finding the roots of a function. How do I find the roots of a function? Your head should probably immediately go to like a Newton method. So that's the basic idea. If you want to solve a game like this, your first instinct should be, okay, to first order, a necessary condition is these KKT conditions. So how do I solve them? It's a root finding problem. I should think Newton method. And now I'm going to shortcut over all of actually solving the problem. I'd love to talk about that. I'm very happy to, but that's I think beyond the scope for today, at least to understand the meat of the talk later. But anyway, that's kind of how to think about solving them. Now there is some subtlety, and beyond the subtlety of actually solving them, I always like to point out that when you design an algorithm to solve a game, or really any decision problem, that algorithm is making some maybe subtle assumptions about the information that players have access to when they make decisions. And so in my experience, this is an easy thing to get wrong. This is an easy thing to misunderstand and come to some very wrong conclusions about. So I always try to point this out in talks that I give. But if I write down KKT conditions like I did before, it turns out that these conditions define what's called an open loop equilibrium. So what that means is that it's the kind of set of strategies that I'm kind of imagining each player has access to are ones which only depend upon information that each player knows the initial condition and the time. So again, it's a subtlety, and I don't want to dwell on it too much in this talk, but I kind of do want to point out that anytime you talk about a decision problem, and particularly you talk about a game, it's important to understand that the solution you find is going to encode some information structure, what information players have access to at what times. And in this case, basically for the rest of this talk, I'm going to be talking about open loop equilibria, which are defined by these KKT conditions. We've done a fair amount of work to try to also write down actually much more complicated KKT conditions that correspond to like feedback strategies. So if you're at all interested in that, I can talk about it. But anyway, a subtlety to know. The upshot of all of this is to say you can solve these root finding problems, whether it's in feedback or in open loop, easily in real time for sort of modestly scaled problems. So this was just some early work that I did at the end of my PhD. Sylvia will remember when this was going on very well, but basically, like I remember flying out to this airfield in the middle of Washington, putting like an early algorithm for solving these problems on a test plane and just sort of autonomously taxiing around the airport and avoiding taxiway intruders and stuff. So you can easily code up these algorithms to solve these root finding problems quite quickly. So that's maybe a big plus. Okay, so I think that brings us to the point where we now have all the tools to understand the main topic for today. Um, so this is the title of our paper that I mentioned from Wafer, and it's only 5 words, but there's a lot going on. So let me try to break it down. Um, so we talked about games just now. This paper is about inverse games. So an inverse problem is one where basically there's some parameter of the problem and you don't know what that you'd like to know what that parameter is and sort of discover the parameter value by looking at the solution to the problem. So what I mean is in a game, like an inverse game is the process of trying to identify what were players' objectives by watching them play the game. Okay, so solving the games like we just talked about, these root finding ideas, I had to write down what game was being played. I had to write down the objective functions and stuff and constraints. In these inverse games, I'm interested in identifying what are those objectives and maybe those constraints by watching equilibrium play. So what we'll see is that actually the kind of state-of-the-art existing best understanding of those problems is deeply tied to maximum likelihood or kind of map estimation, so point estimators. And in this paper, we're going to construct a kind of a Bayesian technique for backing out some approximation of the posterior distribution over those hidden objective functions. So that's the main topic. And then the autoencoding bit is just a pointer to us using some autoencoders. So all this will hopefully become clear, and I want to give credit to the students who drove the work, Shinjae and Lhasa. All right, so that's where we're headed. But kind of my last aside before we get to the meat of the actually talking about that inverse game problem is our technique also relies upon this very interesting observation, which is that Nash equilibrium solutions to games are basically differentiable with respect to parameters of those games. I'll unpack this a bit more on the next slide, but you can kind of think back to like basic calculus. Everybody knows like equation of a unit circle, x squared plus y squared is 1. If you differentiate both sides with respect to x and then rearrange, you can get an expression for the slope at any point on the circle, right? So hopefully everybody's kind of seen that at one point in life. We're basically going to be able to play exactly the same trick on those big, nasty KKT conditions. So here's how that looks. Suppose the game solution is just that collection of primal and dual variables. I'll collect them into the variable tau. And suppose it depends upon some other kind of hidden parameter theta. So maybe theta parameterizes the objectives of the agents. Maybe also the constraints, the physical dynamics of the game. So all I've done is I've just rewritten the KKT conditions and color-coded everything nicely. Okay. So playing those kind of implicit differentiation tricks, we can get here. So what I do is I have this equation G tau theta equals 0, and I take the total derivative of G with respect to theta. If I do that, I get the expression I wrote, and rearranging, I can see that the derivative of tau, the equilibrium, with respect to theta, the hidden parameter, is just some expression. Okay, and I'm pointing out that look, there's a matrix I'm having to invert. Gee, I guess like maybe that matrix might not always be invertible. There are some caveats. Okay. We can talk about the caveats if anybody is interested, but the upshot is you can differentiate solutions with respect to parameters. All right, this is how to do it. Okay, and if
Can I
you're
ask a question?
Yeah, go for it.
So when you have a undefined gradient here, when it's non-invertible, does that mean like your strategy set diverges or something?
No. Well, okay, actually, so there's some hidden stuff going on. So there's a lot of hidden stuff going on. So one possibility is what you're saying. So if that was going on, actually, the way that would manifest is you couldn't even solve the forward problem. So with like going back to the circle slide, that would basically be saying like, okay, if I move a bit horizontally, like imagine the horizontal axis here is theta and the vertical one is tau, so like x is theta, y is tau, then, or maybe other way around. Yeah. Anyway, whatever. What it's saying is like if you change theta a little bit and then there's no solution to the problem, that would be like this curve, the unit circle sort of not being well defined for some values on the horizontal axis. So that would certainly break our implicit differentiation, but it would break it for the reason that the function is not even well defined there. So it's an implicit function and it's not necessarily well defined. I mean, I didn't even talk about conditions for existence of Nash equilibria, but yeah, it is possible that the function is not defined for all theta. But maybe
I see.
maybe it's not even a proper function. Just like this implicit function is, like I plug in a value of x and then there might be two values of y, so it's not properly a function. So anyway, you can kind of have the same issues arise in the Nash equilibrium setting, but actually like the issue that is arising when this matrix drops rank that you're trying to invert, that's telling you something else. So that's telling you that basically the manifold that is defined by the function g equal to 0 drops rank, drops dimension. So this manifold is like some surface in whatever dimension space we're living. And if that surface at some point theta drops dimension, that's this matrix dropping rank. And so when that happens, the derivative d tau d theta doesn't exist. But what does exist is if I pick any direction in the space of all thetas, I can ask how, I can certainly compute how does tau vary along that direction. So that's a directional derivative. And I can definitely compute that thing. So that's basically the caveat. So when this thing drops rank, basically you end up having to pick a direction and you can compute the directional derivative.
I see. Thank you so much.
For sure. Okay, and kind of part of why I mentioned this is just to throw out a little advertisement that if you're interested in trying out any software for any of this in software for yourself, here's a nice little package that it's nice open source. It's a solver for exactly these problems. Mixed complementarity problems is sort of the more general name. Complementarity because of KKT conditions complementarity. And this is just my little implementation of it. It's easily hackable. I don't make any claims of it being perfect, but it's nice, and it does support this implicit differentiation through auto. So it plugs into existing chain rules packages for Julia. So if you're interested, maybe check that out. Okay. Okay, so this brings me to the good, the real point of today's talk, which is this inverse game problem. So here's the running example. Think about an intersection. There's a robot approaching the intersection. They see an oncoming vehicle. Maybe it's driven by some human driver, and the robot knows where it wants to go, the kind of red diamond, but it has no idea what the human's goal is. So here, this human's goal, this is a variable theta, and it just let's just say it's a position in the plane. So it's R2. Okay, so then the question is, how do I figure out what is the right value of theta by watching the human drive? Okay, so the way we would understand this problem is we'd say, okay, if I knew theta, then I would solve the game kind of forward, and I could tell you maybe what a Nash equilibrium solution looks like, and that would define a trajectory for each vehicle. And maybe there are multiple equilibria, and maybe there's no equilibrium for a particular choice of theta. Like, this is more complicated than I'm making it sound, but for the sake of one lecture here, let's just pretend we can solve this thing uniquely as an example. So sure, if I know theta, I can solve the game, I get some trajectories. The inverse problem we're interested in here is if I get, let's say, some noisy partial observations of that behavior, those trajectories, let's say that's this variable y, how do I kind of go backwards and figure out what's theta? So the way we kind of do this in the literature in this area is we write down a problem that looks like this. We say, okay, I want to estimate theta, which maximizes the likelihood of observations under the constraint that the trajectory, which I'm sort of modeling those measurements coming from, arises as a Nash solution to the game parameterized by theta. Does this make sense? Okay. So then, computationally speaking, this constraint is complicated, but we can kind of to first order replace it with the KKT conditions that we saw already. And now I have a problem where, basically tau depends implicitly upon theta, but I just showed you how to differentiate differentiate tau with respect to theta implicitly on the last slide or whatever. So now you can pretty easily chain rule through the objective and basically just take gradient descent and solve this problem. Okay, so that's kind of the basic way that people think about solving these problems now. And what we're interested in this paper is going away from this point estimation view of sort of just coming up with a single best estimate of theta, the hidden parameter, and instead try to understand what is the full posterior. So why are we caring about the posterior? So for example, in this illustration on the left, what's happening is the human is just approaching the intersection, and basically they've been going straight up until this point. So because we know that, I guess I can see that I'm trying to indicate that they're starting to turn a little bit. What this tells me maybe is like they're probably not going to turn right from their perspective, right or left, the robot. So, maybe there's a chance they want to go straight, and maybe there's a chance they want to turn the other, the way I've indicated here. And so that would, maybe give me some probability density over the positions in those two lanes of where I think they're trying to go, as an example. So that's what I'm trying to illustrate here with this posterior. And once I know that, I can maybe use that information to generate a distribution of trajectories that they might be planning to drive. And maybe with that distribution of trajectories, I might be able to plan more sort of safe trajectories for myself, the robot, to not get myself in trouble. Okay, so as an example, like what we'll see kind of one of the results I'll show you at the end of the talk is that if I kind of go with this maximum likelihood sort of point estimator of theta, I might be overconfident, right? I might sort of be just planning as though I'm certain that I know what the human is trying to do. But if I'm wrong, I might be committing to a course of action that I can't recover from. Yeah. Okay, so that's kind of the circumstance we're hoping to be able to avoid. Okay, so how do we do this? Basically, the right thing to do is to think about Bayesian inference. And if you think about Bayes' rule, I've just written it out here. There's some kind of classic challenges everybody who's stared at this, will probably be thinking about. So the first challenge is every time you think about Bayesian estimation, you have to think about what's the prior. Knowing the prior, obviously, you can stare at the equation. It's going to influence what the posterior is. And if you don't know a good prior, that's kind of limiting your ability to synthesize observations and data in order to get a posterior that's useful. So the better your prior, the better your posterior. Now, specifically in our case, we can look at this other term, the probability of the measurement y given the hidden parameter theta. In order to evaluate this likelihood, we have to actually solve the game. We have to be able to map from the parameter theta to the equilibrium tau, which recovers, which our sensor model can then map to measurements. So that's kind of complicated. So that's something we'll have to handle. And then the other kind of very common thing people understand in Bayesian estimation is that this marginalization is typically intractable. So in this case, I'm illustrating a sort of a planar example where theta just lives in R2, and maybe this integral is something you could compute numerically, but try doing this in higher dimensions, it's not going to be fun. So typically people are, looking for ways around this marginalization. Okay, so this brings us to the insight, which is to say that actually in practice, maybe I don't actually need the full posterior in order to, like maybe I don't need the closed form of p theta given y in order to use it effectively for planning purposes. So in practice, maybe drawing samples from this posterior is enough. And if that's the case, then we can try to uh, learn some kind of generative model, in our case, a variational autoencoder that basically allows us to generate samples from the posterior. So that's essentially what we do. I'm going to kind of, I think, show you how to construct this thing, and I'll skip over all the details of training because they're essentially identical to any standard PAE training pipeline you can get from a textbook. But so to me, that's not the interesting part. So anyway, how do we build this thing? Well, that forward game on the top, that's just the differentiable game solver that I showed you before. Maps from game parameters to game solution, and it's differentiable, so you can backprop through it. And then the inverse problem looks, the full picture looks like this. So what you do is you sort of take your observations, you can push them through a neural network that's going to encode them into a latent space. In the latent space, we'll kind of force the distribution of that variable z in the latent space to be normal, where the mean and covariance are going to be kind of the output of that encoder. So in other words, I put in an observation and I get a normal distribution in some latent space, some space that has no physical meaning. Then I can sample in that from that normal in the latent space and pass through a decoder. It's another neural network we'll train. And because it's a neural network, it can be wildly nonlinear. The samples that are normally distributed in the latent space can become as arbitrarily multimodal as you need. So that means, in our case, we had a bimodal I was sketching a bimodal distribution for this posterior p theta given y. That could easily arise with a nonlinear kind of neural network D here. Okay. And then once we've kind of pushed those sampled values of z through the decoder to get corresponding values of theta, each one of those values of theta maps to a solution to the game tau via this differentiable solver. And then we have to assume we know what sensors we have access to and the statistics of those samples. So that's kind of this last bit that was on the right. So sorry, I prematurely did that. So that's that last bit. Oh gosh, why is it doing this? Okay, my mouse is not visible to me, so probably not to you either. Anyway, so I said I would skip over how to train it, but the basic idea is you try to kind of match the distributions induced by these neural networks to basically to distributions that you should expect. And so that induces like there's a loss function that describes that sort of mismatch in distribution, and you can minimize a lower bound on that cost. So that's the basic idea. Anyway, once we've trained it, in order to actually like sample from the posterior, all we do is we just take the observations, pass them through these the encoder, sample from the normal in the latent space, pass through the decoder, and that's pretty easy. That's just passing some stuff through some neural networks and sampling from a Gaussian. That's very, very easy. So you can do that in real time, no problem. Okay, so let me pause for a second, check the time. I think we're doing well on time. So that's basically all I wanted to say about the method. Is it kind of clear to people? Any questions?
I have a quick question, if you don't mind, Professor.
Yeah.
Can I go ahead?
Yeah, go for it. Go for it.
Oh, this might be a very basic question, but how do you force a normal distribution in the latent space?
Oh, so it's by construction. So basically, if you look at the bottom of this picture, what I'm doing is I'm passing some vector y into a neural network, and I'm interpreting the outputs of that neural network as the mean and covariance matrix of a normal distribution. Okay, so it's literally, I mean, I'm just interpreting them that way, and you have to be careful. You have to make sure that actually like the way the output is interpreted as covariance is positive semi-definite, right? So okay, like some subtlety, but the point is, you can sort of just um, like rearrange all the numbers that are coming out of that neural network into a mean vector and a covariance matrix, and then sample from the corresponding distribution to the corresponding normal.
I see.
Yeah.
Thank you.
Yeah, for sure.
How sensitive have you found this to be to like the size and structure of the networks?
That is a great question for my student Shinjay.
Okay.
And my recollection is that he never even mentioned it to me. So I'm interpreting my inference there is that he did not have any trouble with it. But yeah, I don't have a better answer for you.
David, just chiming in as well. How sensitive is it to mode collapse, which you would typically see in like traffic models with normal latent space, which you sample from? Is there any
Yeah.
to get the bimodality back seems non-trivial sometimes.
Yeah, that's a good question. I'll kind of give the same answer. It's not something Shinjay ever told me about, which means I don't think he ever had a problem with it. I will tell you one other thing, which is my understanding, again, maybe it's a better Shinjay question, but my understanding is that mode collapse is a much more prevalent issue with other types of generative models like GANs. And it's less like one of the reasons people prefer VAEs to GANs is because they don't suffer from mode collapses readily.
Okay, yeah.
Yeah,
Cool, thanks.
for sure.
Can I
Okay.
ask another question? Oh,
Yeah,
sorry.
go for it.
I imagine this gets trickier, so feel free to brush it off. But like, if you did want to consider a distribution over the game parameters, could you solve a distribution of the game solutions as well, or does that get tricky?
Okay, let me try to make sure I understand the question. So what you're saying is, could I also directly solve for a distribution over the equilibrium trajectories and not just over the parameters?
Yeah.
So I think that is actually like, okay, I guess I'll give two answers. The first, like, to me, like straightforward math answer is if I give you the distribution over theta and I give you the solver, you can easily get the distribution over tau. Right? You just sample from the distribution over theta and pass each sample through the solver, and you get another set of samples for the distribution of tau. So I think that's like, easy answer one. But then maybe like more important answer two is that if I give you measurements and like your sensor doesn't suck, then that probably gives you a pretty good idea of where the trajectory was. So like, put it another way, like state estimation in the sort of traditional sense of like localization and mapping or Kalman filtering is just like way easier than this. And the reason it's way easier is because the like nonlinearities you see in sensors, like the worst one people typically talk about in this kind of context would be like range and bearing measurements or something. It's like not that bad. So it gets bad if you're talking about like, I don't know, observing satellites in orbit and you only have range measurements or something. But come on, for a car, like this is peanuts. Nobody has trouble estimating where the cars are on the road unless you're Tesla and you have no sensors. So so like the reason this problem is hard is because the map between theta and tau is complicated and very nonlinear because those KKT conditions are very nonlinear. Does that make sense?
Yeah. Yeah, it seems like to me that there, maybe I guess the difficulty that I would wonder about is like if you don't have enough data to really distinguish two different or like completely different trajectories in the long
Oh,
horizon or something.
yeah. So if
Um,
you don't, if yeah, okay. Oh, I see what you're asking. So like actually, basically what's happening is in this situation I've illustrated on the left-hand side here, like you only see the yellow part for the humans. So you can't distinguish if they're going straight or they're turning very well. Um, so yeah, so basically that I've the way I've kind of written this problem, I haven't been super crisp about it in the same way that we are in the paper. But if you consider the trajectory that you're trying to estimate to include the future, things that you haven't seen yet, then yeah, that could very quickly, you know, uh, that could very quickly be a complicated object to be estimating because, yeah, maybe it depends upon control decisions that are have yet to be taken, right? So on the other hand, I think the way to understand it here is that those decisions that haven't happened yet, we're modeling them as arising from equilibria of a game whose players' objectives, we just don't know. So if I estimate those objectives or the distribution over them, I can predict what the future trajectories will be.
Thank you.
Sure. Okay, so I kind of just want to close out by showing you some sort of typical results we're getting with this method. And
I'm
just,
sorry, David, can I ask one more question?
yeah, go for it.
If I throw in a third car now,
Yeah.
do you have to retrain everything or can you handle?
Yeah, you have to retrain. So you basically have to retrain. And that is like a pretty obvious like important direction to be pushing here. It's not ideal to have to retrain. Yeah. Okay. Although I will say, I have a student who's working on something very related to that question, so I'm happy to talk about that afterward. Okay, so just to kind of illustrate how this thing works, I guess the main uh, thing I want to compare it to is like that point estimator I started with, the maximum likelihood thing. So what I'm going to show is the exact same starting point, um, and um, and what's going to happen is the oncoming vehicle coming down from the top actually has a ground truth, like desired goal position, which is that green diamond. Okay, so that's the same in both left and right. And the way that I'm going to model that decision maker is I'm going to model them as playing a game where they know our robot's goal. Just it's a clunky assumption, I know, but I'm going to just model it that way for now. So basically, I'm going to have them solving a game where they know what we, the robot, want, and they, of course, know what they want. So they know where our goal is, the red diamond, and they know where their goal is, the green diamond. They're going to solve for a Nash equilibrium. So whatever time it is, they're going to solve for the Nash trajectories, and they're going to execute their first action, their first control. Okay? So that's what's actually going to unfold, how they're going to make decisions. But how are we going to make decisions? So I need to tell you about the planar that we're going to construct that can consume this kind of samples from the posterior over theta. So this is just the simplest thing we could come up with to illustrate how to use these samples. There could certainly be other more intelligent things you might imagine, but this is at least enough to illustrate the point. So look on the left. I'll just kind of start to play this and then it'll pause and highlight some things. So what we're doing is I'm looking at the yellow dots. Those are the sort of noisy measurements of where vehicles have been. That's Y. I'm pushing Y through the encoder, sampling from the latent space, and pushing each sample through the decoder. Okay, and I'm doing that, I forget, let's say 100 times, and plotting those things as those two blue clouds. Okay, so basically what you're seeing is this posterior is obviously bimodal, and it has some additional kind of, like each cluster has some structure to it. We're ignoring the structure, and we're just gonna like cluster this thing, all these samples into two clusters. and take the cluster centroids. That's the green stars. Okay. Okay, so given these two cluster centroids, I'm
Wait,
going to
can I ask
now,
a quick question?
yeah,
Um, so it looks like, at least just visually, there are more samples over here than over here.
yep,
But
true.
the MLE still believes that it's likely to go straight still. Is that how I should be interpreting it?
Uh, okay, actually, there's one other subtlety, which is that this MLE, we're actually only taking gradient steps on that MLE problem, and I'm just showing you
Okay.
so that it's a little, I wish
Okay. So
it
it's
was not.
moving in this direction.
Yeah, exactly.
Okay, okay.
Okay, so yeah, that's a good point. Um, that's a great point. Okay, but anyway, back on the left, what's happening is we have these two cluster centers, and I'm basically going to construct like I, the robot, I'm going to imagine two copies of the human, the oncoming vehicle, one that wants to go to cluster one, the other one that wants to go to cluster two. So now there's three players in this game. The two copies of the human are not going to interact with each other, but I, the robot, am going to interact with both of them and try to basically optimize for average performance and enforce collision avoidance with both. So that's the simplest planner we could think of that would consume this information. And so we'll solve that three-player game. We'll look at our first control action and take it and then resolve the next time step. Okay, so that's kind of how this is going to play out. On the right side, it's exactly as Sylvia just pointed out and I hopefully clarified. So what I'm showing is I'm starting the initial guess of theta at just that they want to go straight, because that's probably where it would have been if I had seen them coming straight down. And then every new data point I get, every new observation from the next time step, I basically take a couple gradient steps on that MLE objective, and I'm plotting those as the little green stars. Okay. So, of course, what's going to happen is as the car starts to turn, there's going to be more pressure on that. The gradient is going to get bigger to push this green star towards the green diamond. All right, and that's what you're going to see. So let's kind of unfold. Okay, and I'll play it back. Okay, so playing this back, and oh god damn it, come on. Okay, right. So what you're seeing on the left, where I paused it, is when the vehicles get close, we are still far enough away that we are not at risk of collision. We can kind of slow down as soon as we realize they're going to cross our path. Whereas on the right-hand side, if I kind of, god dang it, if I replay this stupid video, I hate this interface. If I replay it, what's going on the right is like, okay, by the time my MLE realized, oh shoot, they're actually turning, I'm now in this sort of, I'm well into the intersection going pretty darn fast, and I'm now having to take some evasive action that's dangerous. So yeah, so it kind of leads to this awkward maneuver. So just to illustrate, the point is just to illustrate that if I'm keeping track of kind of the full multimodality of this posterior over players' intentions, even in this simple two-player context where there's only like one unknown objective, it's not hard to construct scenarios where I can actually use the posterior, the full posterior productively to interact better.
Can I
Does
ask
that
one
make
more
sense?
question?
Yeah.
Can you remind again what the diamond or whatever the shape is is here and why it was moving around and why it's over here right now?
Yes, because we're always choosing two cluster centers, and I guess there must be like one very small blue dot that this is probably sitting right on top of. So it's
Okay.
just some artifact of like we sampled 100 points or 1,000 points in the latent space and then mapped them all through the decoder. And one of them must have ended up over there.
Do you ever see the clusters being, I guess intuitively I would have expected at the end of the video there to be two clusters just very close to each other. Do you have some?
Yeah, so that probably is happening. And again, this is a Shinji question that I
Yeah, yeah, I
expressly
understand.
embarrassed. They don't know the answer to. but like you can kind of tell. I guess I didn't explain like what the red and the green things were either. The like trajectory dots kind of coming out. So if I kind of rewind, what you can see is like there's from this human vehicle, there's like the two copies. We're kind of envisioning like
Yeah.
two red plans trajectories they might have. The green is what they're actually going to do. And so, if I fast forward enough in time, at some point we like realize, oh, actually, yeah, this kind of second option, they would have to slow down to avoid collision. And then at some point we realize, oh, actually, I think he must have just had some logic in there that's basically saying um, that like there's this dummy cluster that probably has so little
I see.
mass that it's just ignoring it. I don't exactly remember how he handled that. But
Sure,
the
sure.
larger point I'm trying to make with all this is just to say, like, even with some pretty dumb construction of a planner, it's not hard to like use the information in a way that yields better interaction. So hopefully that at least comes across. Okay. And then the last kind of result I'll leave you with is just to show that, yeah, you can do this for more players. You just have to train a different VAE per Sylvia's question earlier. Training that thing is more complicated because now there's more players, which means the game solver has to do more work because the number of variables is dramatically increased. So we're solving a root finding problem to solve that game every sample. That is like typically like cubic in the number of variables. So if the number of variables scales with the number of players, you can kind of figure out the scaling there. It's not so hard. But the upshot is you can still do it. And here's like what happens in this little case. Okay. So anyway, I guess the take-home message I'll sort of try to conclude with is just to say that because Nash equilibria are at least directionally differentiable with respect to parameters, we can kind of exploit that differentiability to learn, approximate posteriors on these hidden variables. And then one can pretty easily construct planners that consume that multimodal information to better interact safely despite the uncertainty. So hopefully I've left you with a clear message. There's a lot of hidden details that we didn't have time to dig into as much as I would like. And so, I don't know how much time we have left. Hopefully, it looks like at least 10 minutes or so. Do we, Sylvia? Yeah, so I'd love to take questions, anything you like.
Thank you so much, David. All
Certainly.
right, yes, questions from the audience. Maybe while people are gearing up. So the questions I've been asking to all presenters is first, when is this a good method to use, and when is this not a good method to use?
Good question. I think it's a good method to use. Okay, like maybe it's easier to say when is it not a good method to use, or what are the limitations? Like we're fixing the number of players, so that's a huge limitation. So obviously it's a good method to use if you know the number of players, and it's not a good method to use if you don't know how many people you'll be interacting with at training time. So that's a pretty obvious one. I think other kind of obvious issues with this method is we're kind of parameterizing the structure of the game. So all players' cost functions and constraints and anything else that depends on theta, we're assuming we know that parametric family beforehand. So personally, I don't view that as a terrible assumption. I think it's a very practical one that people make all day long in any remotely practical setting. You make those assumptions. So go talk to anybody doing motion planning at any AV company or other kind of autonomy company, and people are making those assumptions all day long. So personally, I don't view that as a problem, but I think it is theoretically a concern. We're assuming we know the sensor model. I don't think that's bad. I kind of glossed over the complexity of training, and Sander asked a good question about it that I think it's legitimate. You could have mode collapse. Training is not trivial all the time. So those are some limitations. But I think broadly speaking, what this is great at is it's great at capturing multimodal behavior. And so in that sense, we haven't, we've been very happy with it.
Yeah, and I know you touched on this, but it's worth emphasizing to people who might not be as familiar that doing this Bayesian inference is really hard. And
Yeah.
so anything that improves on that is a big deal.
Yeah.
Okay, are there questions yet from the audience? Or should I keep going?
Sounds like it's all you, Sophia.
I have a quick question. That demo GitHub that you showed earlier, what kind of examples would we find on there?
So I think I put in two examples. So first off, like this was just like I was bored over Thanksgiving holiday and I started coding this up. Actually, I was bored during somebody's defense, I won't say whose, and I started sketching it out. So anyway, the point is it's what it is it's a general solver. I didn't want it to be specific to any like exploit any structure of trajectory games or anything like this. So the two examples that I've cooked up, like I cooked up just a very easy like quadratic game, yeah, basically like a linear complementarity problem. So if you think of like matrix games, like there's an example for that.
Mhm.
Actually, it's a whole benchmark, Monte Carlo benchmark, so you can sort of compare it to other solvers. And then the other one that I have in there is actually like sort of one of these trajectory problems, so just like some lane changing. So that gives you a
Oh,
little,
awesome.
yeah.
Very cool. Okay, I'll check it out. Thank you.
Yeah, have fun. Yeah.
Okay, that segues me nicely into the next set of questions that I always ask, which you've already touched on, and I know you already gave us your text. And someone is very, very excited after watching this, and they want to dive into both understanding the theory as
Yeah.
well as understanding implementation and tools. Where would you recommend they go to?
So I think for the theory, I think the text is intended to be a very gentle introduction to the theory, but by no means a complete one. So I have pointers in there to, more complete resources on a lot of the different topics. Some of those are papers, most of them are textbooks. So I'll just like pull out some of the textbooks. I just have them here. So yeah, here's a couple of them. So if you want to know more about like the basics of optimization, this is the place to start. Numerical optimization, very accessible. It's like got enough theory to help you understand where things come from, but also it's practitioner oriented, quite algorithmic, etc. So I recommend this. It's a very well written book. Read it cover to cover. You'll enjoy it. You won't regret it. If you find topics in there that you want to learn more about that they don't cover, this is the next book. So that's also great. Would highly recommend. Then if you love that stuff and you want to see how it applies in kind of the mixed complementarity problems, sort of the game setting, this is where you should start. So this is also a fantastic, it's actually a 2-book series. I'm just showing you volume 1. Volume 2 is about algorithms. It's quite a bit denser than the other two. So be warned, but I think at least the first chapter is quite accessible. And it's worth having a copy of if you're interested. And then if you're interested kind of in more dynamic
Sorry,
yeah.
who was the author on that, David? I couldn't see with the resolution. The author? Is it okay. Oh, that's a tough one.
Yeah,
I can ask David for this list
yeah,
after.
so it's Francesco Pacini and Zhongxi Peng. Zhongxi Peng is actually at USC, so not far from you. Okay. And then if you're interested in dynamic games, so I had this one slide kind of picking out differences between open loop and feedback information patterns. If you're interested in some of those subtleties, if you're interested in kind of equivalent, like just a lot of great, like shockingly subtle theory behind dynamic games, this is the book for you. So this is a great book to have on your shelf, and again, read cover to cover. It's a good one. Every time I open it, I learn something new, even though I have read it many times. So in particular, like just because I know who I'm talking to here, if you're ever wondering about like pursuit evasion games and you want a much more like accessible yet I think quite deep introduction to like what is going on in those games, guess what? Chapter 8, Pursuit Evasion Games. Very, very good book. Very good chapter. I learned a lot by reading it that after doing a PhD on these things I didn't know. Anyway, those are good resources. Software. I have kind of fallen in love with the Julia language. I think there's a lot of good tooling in there, but I also I think in my PhD I was working a lot in implementing stuff in real time, kind of robotics, ROS, etc. So C++. Anyway, so there's good tools in multiple languages, and I'm happy to kind of point people towards resources if you have more specific questions there. I don't know. Hopefully that kind of gives it back.
I forget in the paper, do you have a link to the code? Is that public yet?
Which code?
For the
So this
paper.
one, the QR code will get you there. I don't have it in the oh, you mean for this paper? Yes, sorry. Yeah, there should be a link. Yeah, it's public.
Okay, great.
I hope. If it's not, tell me and I'll bug Xingje to open source it.
It is. So.
Okay, cool.
Okay, and then I guess I'll also ask the last set question, which is kind of what do you see as like big open research challenges that remain in this area?
There are so many. I would say like some of the more interesting ones to me are how do you deal with kind of uncertainty in the information that players have access to. So let me give an example. So like there's a great paper. I don't know, Sylvia, did you ask Jaime to give a guest lecture?
Not this year.
Not this year? Okay, surely in the past. Anyway, but Jaime had a great paper, came out at this point probably 4 years ago, at least, maybe three, but in RSS. And basically they're studying this problem of how do I overtake somebody on the highway? Well, if I'm overtaking somebody on the highway, if it's like a one lane each direction sort of country, remote highway, you typically need to be careful that there's not an oncoming car. So like, if you've ever been in this situation, you'll know like what you do is you wait for a long straightaway and then you duck out and you peek. And if there's no oncoming vehicle or if they're very, very far away, you quick accelerate and overtake. Otherwise, you see somebody or, you can't see around a turn or something and you duck back behind. So what Jaime basically did is he expressed this interaction in terms of coupled feedback and open loop games. So basically, when you can see the oncoming vehicle, you have feedback information. So you know that the next time step you'll have access to sensory information of where they are, and you can use that to make better decisions. And if you can't see them because they're occluded, you're in an open loop information pattern. And so they were able to basically stitch these things together and solve some reachability problem, basically. And so that's a great example of a problem where the information available to different players is varying throughout the interaction. And what's even better about that problem that was sort of the basis for how they constructed the solution is that, well, actually, there's enough structure to how that information availability is changing as a function of state and time that you can solve it. A lot of partial information games you can't solve. One thing that I find exciting is that it just happens that is also a game in which, we can extend what they did to basically use some of these tools I showed you today to actually like not be restricted to solving it with the IPDEs, but you can actually just solve the KKT conditions directly and go from exponential complexity to polynomial complexity and do it in real time. So like, and it necessitates a different algorithm. There's different analysis of the algorithm. It's not trivial, but it's also elegant. And I think these questions of basically how do you solve games where players have access to sort of varying information over time is very interesting to me. The inverse problem is also really cool. Like, how do you estimate what information players have access to based on watching them act? Um, so anyway, hopefully that gives maybe some indication.
Yeah, great.
Yeah.
All right, we have time for maybe one last question. Anyone?
Yeah, I guess more practically, so coming back to the main paper you presented today, the training is based on these dynamic game rollouts where we have access to the underlying parameter that guides the opponent, right?
Yeah.
In
Oh, hold on. So yeah, hold on. Let me think about that. So the training data is we just had to have trajectories. We did not have to have the ground truth um, intentions. Is that correct?
Yeah, but the
Yes.
trajectories are based on a fixed sample of a ground truth intention, is at least what
Yes, that's correct. That's
yeah.
correct.
In then taking this, so I think there indeed the mode collapse issue doesn't appear as prevalently because you can create mode diversity in your training. But in taking this to a setting where where the multimodality might be more scarce, I'm wondering whether starting off like pre-training it on a setting where you have a lot of modality that you've self-infused, and then kind of updating the modalities based on actual driving interactions that you've observed, whether that would potentially be a way to preserve multimodality considerations instead of trying to learn it from scratch from just a way behavior that is relatively unimodal. What
Are
are
you
your
saying basically
thoughts on that?
overweight rare events or rare data values?
Well, leveraging in a way, creating artificial data that has this multimodality in addition to largely unimodal data that you see when you just take real life data sets, such as a Waymo data set, whether that could help the issue in like motion planners that are just based on data,
So I
if
think
that makes sense.
I guess I don't fully understand the suggestion you're making, but what I would maybe say is like, I just want to emphasize like the training data we're assuming we have access to is not labeled with the intention theta. So like you can totally look at like the Waymo data set, which like how is it going to have theta? Like this is just some modeling construction we've got that Waymo like how like it's just a modeling thing. Like there's no ground truth. Um, so like so the point is we don't actually need that value of theta, and so therefore we definitely don't know, like we don't need the training data to have multimodal thetas because we don't even need there to be theta anywhere in the training data. So I'm sure that there is some connection that we do need to have some diversity of trajectories we've observed, but it's not clear to me like how that maps onto the multimodality in theta.
Okay,
If that makes
cool.
sense.
Yeah, I might follow up offline.
Yeah, happy to follow up.